Hi everyone, thank you very much for the invitation to speak here to the organisers. I'm listed on the list of organisers and I did literally nothing. I hope you'll forgive me for speaking in English. I prepared the course in English and didn't think, of course, that it might be sensible to give it in French, but it exists. Please stop me if I speak too quickly, tell me to slow down. Please interrupt and ask questions whenever. To the adults in the room, or the grown-ups if I can put it that way, this course is not for you. I'm sorry, you won't learn anything new. But my hope is to introduce the younger people in the room to a field that I find fascinating and beautiful and wonderful, and I hope you will too. So I'm going to be speaking about scaling limits of random trees and random graphs. And I want to start by not being able to move my slides. That works. Brilliant. Thanks, Jeremy. Okay, so I want to start by talking about binary trees, because I hope that this is going to be a setting which feels sort of familiar and simple enough to everybody that we can really make some progress with it before doing things more generally. Okay, so I'm going to let Tn be the set of planted plain binary trees with n leaves. So nobody seems to agree on what these things are called, so I've just put the maximum number of descriptors in the name of this thing. By plant, I mean I've simply stuck an edge at the bottom here. So this is going to be, my tree is going to be rooted at the bottom of the plant. Okay, I've got n leaves. The plant doesn't count as a leaf. And I'm going to have n-1 internal vertices. Okay, so in consequence, there are 2n-1 edges. So I hope it's obvious what I'm talking about here. Please stop me now if it's not. Okay, great. So I'm going to want a second set of trees. So the same thing, but with labels on the leaves. Okay, so I've got n possible places to put labels, and I'm just going to assign one of the uniform labelings. Okay, and the root, which is labelled 0, as I said, is by convention not a leaf. Okay, so we've got these two sets of things, and we can enumerate them. Okay, so Tn, you won't be surprised to learn, is enumerated by the Catalan numbers. Okay, so this is one of the many, many things which are enumerated by the Catalan numbers. And in order to get the size of Tn star, I just need to multiply by n factorial the different ways of assigning labels to the leaf. Okay. So if you do the asymptotics, you see that this is like 4 to the n-1 n to the 3, divided by n to the 3 halves square root of 5. And what I'm going to be interested in is picking an element of Tn uniformly at random and trying to understand its properties. Okay. And it's going to be technically slightly easier to work with Tn star and then think about ignoring the labels later. So what I'm really going to work with is a uniformly random element of Tn star, but the labels aren't going to matter for the sort of properties that I'm interested in. Okay, and in particular I'm going to use Rényi's algorithm to recursively construct a sequence of trees Tn such that Tn for each n is going to be uniform on this set Tn star. Okay, so let's do that. So Rényi's algorithm says start from a single edge whose endpoints are labelled 0 and 1, and then at subsequent steps, pick an edge uniformly at random, divide it into two edges, insert a new vertex in the middle which has an edge with a leaf attached to it with the label n at the end of that leaf, and I'm going to do that in one of the two possible directions with equal probability. So let me just do this on a picture. It's easiest to see it. Okay, so I've got a single edge with 0 at one end, 1 at the other. Okay, there's only one edge to pick, so when I pick an edge uniformly at random, I just get that one. Okay, and I'm going to insert a new vertex in the middle with a new edge and leaf labelled 2. Okay, and I do that with equal probability right and left. Okay. So we can continue in the same way. So I've picked this edge here and inserted a new edge with a leaf labelled 3 in its middle. Okay, so in my picture, sizes of edges aren't going to matter. All I'm interested in is the combinatorial structure. Okay, so 4 goes here, and so on and so forth. So you can see that I'm creating a binary tree which has labels on it. Okay, so my claim is that if you draw this thing in the same way that I started by drawing my trees, then what you get is a uniformly random element of Tn star. So there are various things that I'm going to claim, which checking is going to be an exercise in the exercise session later on. Okay, and this is going to be one of those things. Okay, so this is from a lovely paper Erdôs-Rényi in 1985. Okay, so we've got a way of building a uniformly random element of Tn star. Okay, so a very vague question is, what can we say about it as n goes to infinity? Okay, so let's make that question a little bit more concrete. As n goes to infinity, how does the distance between the vertex labelled 0 and the vertex labelled 1 behave? Okay, so this is something which can only increase as I increase n, but how does it increase? So I want to think about the graph distance. I'm adding new vertices in the middle, okay? And so what's happening is that that path is gradually getting longer over time, every time I add in a new vertex along that path. Right, so the distances in my, let me go back. So the distances in this picture have no meaning. What I'm thinking about is graph distances in the picture on the right. Is that okay? So the distance is 5. 1, 2, 3, 4, 5, indeed. That's possible. Okay, everybody happy? Great. Okay, so first thing is that the total number of edges present in my tree at step n is equal to 2n minus 1. So let's think about the number of edges along this path between 0 and 1, so the graph distance that we have to traverse. Okay, so if I add a new leaf in somewhere along that path between 0 and 1, what happens is that path gets longer by 1. And if, on the other hand, I pick an edge somewhere else in the tree, then nothing happens to the length of that path. Okay? So this is just an urn. Okay, I've got a 2-colour urn. So let's suppose we've got 2 colours, black and white. Okay, the black balls in my urn are going to represent an edge in the path between 0 and 1, and the white balls in my urn are going to represent edges elsewhere in the tree. Okay, so whenever I pick a black ball, whenever I pick an edge along the path from 0 to 1, what do? I add in a new edge along that path, so a new black ball, and I add in an edge that's not along the path, a white ball. And on the other hand, if I pick an edge somewhere else in the tree, I don't have any effect on the path between 0 and 1, okay? And so all that's happening is I'm just adding 2 extra edges somewhere else in the tree, or in other words, 2 more white balls into the urn. So we get these dynamics that whenever I pick a black ball, I put it back in with a second black ball and a white ball. And whenever I pick a white ball, I'm going to put it back in with 2 more white balls. Okay? And we start just with a single black ball. So let's think about the evolution of the number of black balls in this urn process. Okay, so I start with B1 is 1. Okay, for some reason I'm enumerating from 1 just so that I get the label of the edge that I've just added. So the label of the leaf at the top of that edge is going to correspond to the step in this urn process. So it's helpful to enumerate from 1 rather than 0. Okay, so let's think about the conditional expectation of the number of balls in the urn at step n plus 1, given the number I have at step n. So there are 2 possibilities. Either I pick out a black ball, okay, and I pick a black ball with probability proportional to the number in the urn, which is just bn. So there are 2n minus 1 balls in total, and I pick a black one with probability b on 2n minus 1. Okay? And the effect is that I add in an extra black ball. So I get bn plus 1 after this step. And if, on the other hand, I pick a non-black ball, a white ball, then the number of black balls just stays the same. Okay, so if we put all this together, what we get is 2n on 2n minus 1 times bn. Okay, so those of you who are used to looking for martingales will think, aha, okay, we're quite close to being a martingale here. So let's define a deterministic sequence by the following recipe. I'm going to start B1 with 1 and let Bn plus 1 be this slightly weird looking quantity here. Okay, so this is cooked up, and this is another thing for you to check this evening if you feel like it, that this sequence precisely has this relationship. So Bn plus 1 is 2n on 2n minus 1 times Bn. Okay, so in particular, this tells me that Bn on little bn is a non-negative martingale. Okay, we like non-negative martingales. Okay, it's also bounded in L2, so anybody who feels like checking that can check it. Okay, we just need a second moment calculation rather than a first moment calculation. And the asymptotics of this sequence Bn, well, I put Bn plus 1 because it was easier to write down. So this is looking like square root of pi n if you apply Stirling's approximation. Okay, so that tells me that this sequence Bn is looking roughly like square root of n. Okay. And so in particular, if I take my random sequence Bn and I divide by square root of 2n, then the martingale convergence theorem tells me that I get an almost sure limit, something L, which is some random variable. Okay, so I should say that this argument is, or at least I learned it from a paper of Philippe Marchal, who's sitting over there, and it's quite embarrassing to be presenting this in front of a bunch of people who know way more about it than I do. Okay, so what does this tell us? So this tells us that the distance between 0 and 1 is something that when I rescale it by square root of 2n, I get a nice almost sure limit as n goes to infinity. Okay, so it also turns out, and I haven't found a nice, oh, please, go ahead. Just because later I want to be dividing by the square root of the number of vertices. Okay, and it just happens. I mean, I could have chosen anything times, any constant times square root of 2n, and it, square root of n, and it just happens to be convenient to do square root of 2n. So it also turns out that this Bn plus 1 has an explicit probability distribution. So we can actually also think about what its distribution is looking like. Okay, so this is something from this paper here, which has a very nice generating function method of proving this. Okay, but in particular, we can do the asymptotics for this probability mass function. So if I ask what's the probability that Bn plus 1 is about x times the square root of 2n, and let me put the floor in so that this is actually an integer, okay, then this looks like x divided by square root of 2n e to the minus x squared on 2. And that's telling us that not only do we get almost sure convergence to some random variable L, but it tells us what the distribution of that random variable L is. So this random variable L has the so-called Rayleigh distribution. So that's the non-negative distribution, which has got density x e to the minus x squared 2. So the thing that we just got coming out here up to this factor of square root of 2. Okay, so we can understand the distance between 0 and 1 in the limit once we divide by square root of 2n. So we've got almost sure convergence to a random variable with Rayleigh distribution. It's not at all a coincidence. So I'm going to go from the particular to the general. So I just want to start with this example first. We'll talk about more general things later. Okay, so consequences. Distance between 0 and 1 varies as square root of 2n with a nice almost sure limit. What can we say about other distances in the tree? Well, let's think now about the distance from the leaf label 2 to the path between 0 and 1, for example. That seems like the next thing to look at here. Okay, there are going to be more urns. Okay, so if you start at step 2 of Rényi's algorithm, up to this question of whether the vertex labeled 2 is on the right or on the left of the original path between 0 and 1, we always have this picture. Okay? And so in particular, you can think about just looking at these 3 different parts of the tree, and each one of them is going to precisely behave as a little copy of Rényi's algorithm, except that the number of leaves that I'm going to add in each of my 3 subtrees are going to be dependent. So let me draw a sort of more useful picture. Okay, so sometimes I'm going to add in the red part of the tree, sometimes in the blue part, and sometimes in the green part. But if I tell you which labels I added in each of those 3 parts, then I'm getting 3 uniform binary plane trees just with those leaf labels. Okay? So in particular, all I need to understand in order to understand the distances here, here, and here is just how many leaves did I add to each of these subtrees. And that's, again, a 3-colour urn. Okay, actually of a slightly simpler nature. This is really just Pollyer's urn. Okay, so I've got 3 colours, red, green, and blue. I'm going to start with a single ball of each colour, where the red one represents the sort of the edge in the top tree. There's a green one which represents the edge in the side tree, and the blue one representing the edge in the bottom tree. And then whenever I pick one of those edges, I'm just going to add back in 2 new edges of the same colour. Okay? So let's just let Rn, Gn, Bn be the numbers of red, green, and blue balls, respectively. Apologies to anybody who's colourblind. I realise that you can't see this properly, but hopefully the words are enough to also explain what's going on. Okay, so completely standard fact, which again you'll be invited to check on the exercise sheet if you'd like to, that we get the proportions of these different colours converging to a random vector, delta 1, delta 2, delta 3, where this random vector has the Dirichlet distribution, in this case with parameters r. So for anybody who hasn't encountered this before, let me just give you a definition of the Dirichlet distribution. Okay, so it's got parameters alpha 1 up to alpha k. So here k is 3, and it has this probability density which is proportional to x1 to the alpha 1 minus 1 up to xk to the alpha minus 1 with respect to the Lebesgue measure on the simplex. Okay, so we're just sitting on the set of non-negative sequences which sum to. Okay. Yes. Yeah. Yeah. Okay, so how do we get out of this? So what have I given you? I've given you the number of edges in each of these 3 subtrees, and we were actually after the number of leaves. But there's a simple relationship between the two. So the number of leaves in each of the 3 subtrees is simply taken by taking the number of edges, adding 1 and dividing by 2. Okay, so that's straightforward. Okay, so remember that for one of my binary trees, I had a total number of edges 2n minus 1 whenever I had n leaves. So you can see that adding 1 and dividing by 2 is the correct thing to do there. Okay, so if I look at the proportions of leaves in each of these 3 subtrees, I'm again just getting almost sure convergence to this Dirichlet 1/2, 1/2, 1/2 vector. Okay. So if I now look at the 3 lengths in my 3 little subtrees, okay, so approximately they're just looking like small copies of my original urn model, run for a random number of steps, which is approximately equal to n times delta 1 in the first case, n times delta 2 in the second case, and n times delta 3 in the third. Okay, so in particular, it's going to follow that if I divide again by 1 on square root of 2n, what I'm going to get is convergence to, well, the square root of the size of the first tree times the length that I would get in a standard sort of limit of a uniform binary tree, and the same thing in the other two subtrees. Okay, so the deltas are capturing the dependence between the 3 different subtrees. Okay, and then I've got independent component in each case, which is just a new sort of limiting length between 0 and 4. Okay. So we've now understood, let me draw a picture if I can find some chalk. Is there any chalk? So we started off with this picture, and we've now understood how these 3 lengths evolve in each of these 3 subtrees. So we could just keep doing this, okay? But let me, before I do that, just make an observation about these distributions. And again, this is something which is going to be on the exercise sheet. So we can do a little elementary calculation, which shows that I can rewrite this left-hand side. So remember, here I had 3 Rayleighs, and this is the square root in each case of an element of a Dirichlet 1/2, 1/2, 1/2 vector. So one could do a quick distributional calculation to see that that's actually the same thing as taking the square root of a gamma 2 1/2 and multiplying it by a Dirichlet 1, 1, 1. Okay, so that's just a simple calculation you can do. Okay. So, do you want me to write down its density? So it's what happens if you take two exponential one random variables, multiply them by 2, and sum them up. That's maybe a better description. Okay. Right, so and we've got that these two factors are again independent. So there's lots of kind of magical kind of decoupling of the dependence in this problem. Okay, and more generally, if I take the subtree that's spanned by 0 and then the first k leaves, okay, so now I've got a random combinatorial structure that's coming out, right? Because where I add the leaf 3 is not something that I can determine in advance, but let's suppose we went there. Okay, I can do the same analysis on this picture. Okay, I've now got a 4-colour urn model. Okay, and each time we get that, this structure that we get here has so 2k minus 1 edges whose lengths are distributed as the square root of one of these gamma k halves times a Dirichlet split. Okay, so what I want to say about this thing here is this just is a uniform split of this total length up into k pieces. This is what you would get if you took k minus 1 uniform random variables on the interval 0, 1, and then just split the interval 0, 1 up according to where those things land. So I'm somehow getting a uniform split of a square root of a gamma k total length. So let's just observe that the k equals 1 case fits into this pattern because it is the case that the Rayleigh distribution is just the same as the square root of an exponential half. Okay. So where am I going with this? Well, I want to show you what the limiting version of this process is. Okay. So take now an inhomogeneous Poisson process on R plus, okay, of intensity T at T. So this is a Poisson process which has a greater and greater intensity the further right you go. Okay, so if you're not happy with Poisson processes with inhomogeneous rates, let me just show you how you might construct this otherwise. So you can take E1, E2, and so on to be IID exponential half random variables. Okay, and then set the point Ci, so the ith point of this process, simply to be equal to the square root of the sum of the first I of these exponential half random variables. Okay, that's another way of saying the same thing. So I've just split up R plus into kind of infinitely many chunks, which are just getting shorter and shorter as I go further rightward. Okay, so now I want to take those line segments, okay, and I'm going to glue them together in a fancy way in order to get a tree. Okay, so I'm going to start from the first line segment, and then inductively what I'm going to do is I'm going to take the line segment Ci plus Ci minus 1 up to Ci and glue it on at a uniform, at a random point chosen uniformly from the tree that I've got so far. And again, I'm going to have this rule that I'll glue to the left with probability half and to the right with probability half. Okay, so let me show you on a picture. So this is my first line segment from 0 to C1. Okay, and now I want to take the segment from C1 to C2 and glue it on somewhere uniformly at random. Okay, and then I'm going to do the same with C2 to C3, and so on and so forth. So my claim is that this is going to give us the almost sure limit of the subtree that's spanned by 0 and the leaves labelled 1, 2 up to k. Okay, so if I stop this once I've done k steps, that's giving me the same thing as the almost sure limit of that rescaled limiting subtree. Okay, so let's see why that might plausibly be the case. So firstly, the tree at step k has got total length ck, which we said was the square root of this sum of exponentials. Well, that's just the same as the square root of a gamma, as I was saying earlier. Okay. Obviously, the combinatorics of the attachment mechanism are just exactly the same. I'm, again, just picking uniformly from what I've got there, and I'm putting left-right with probability half each. Okay. So the underlying, if I were to ignore the lengths, the underlying sort of binary tree obviously has the same law as the one that we were talking about originally. And then it's just a distributional calculation to show that the cut points and the attachment points give you this sort of uniform split of the interval 0 to C. Okay. So I hope that's at least plausible. Obviously, I haven't proved anything, but I want to kind of convince you that it's reasonable. Okay, So this is the so-called line-breaking construction of the Brownian continuum random tree. Okay, so far we've talked about it up to step k, but I can think about running it forever. Okay, so take the union of all the branches that you get by doing that. I want to think of it as a path metric space, and then take its completion. And this procedure is going to give me an admittedly somewhat informally expressed definition of the Brownian continuum random tree, which is going to be, well, let's say, the key object in this mini course. And for the moment, it should be completely not obvious to you why it has the word Brownian in its title, because no Brownian motions have yet appeared on the screen. Okay, so here's a picture due to Igor. Thank you, Igor. Everybody shows this picture, and now there's only one Brownian continuum random tree, but I want to emphasize that this is a representation of a random object. It might not look exactly like this. Okay. So in the next section, I'm going to make sense of the following theorem. So this is sort of due to a combination of Philippe Marchal and Nicolas Curien and Bénédicte Haas. So if I send n to infinity, then 1 on square root of 2n times my uniform random binary leaf labeled plain whatever planted tree is going to converge almost surely to the Brownian continuum random tree. Okay, so we need to know what sort of objects we're dealing with in order to make sense of this convergence statement. What's the topology in which the convergence occurs, and also why on earth is the thing on the right-hand side Brownian. But before I do that, I just want to record a sort of immediate consequence of the theorem and the way that we talked about our binary trees. So remember that we split our uniform binary plane tree up into 3 little copies of itself, effectively. Okay, smaller ones, but they were sort of, again, uniform. And this property is going to pass to the limit. So in particular, this tells us that the Brownian continuum random tree can be split up into 3 randomly rescaled Brownian continuum random trees. Okay? So this thing is sort of self-similar. It's got little copies of itself inside. And so in particular, that tells you that we're looking at a random fractal. Okay? Okay. So how am I doing for time? Not too bad. So, smiley picture of Jean-François. So if you would like to know more about the things that I'm going to describe in this little section of the mini course, I strongly recommend you go and have a look at this lovely probability surveys paper, which tells you it all in much, much more detail and much more coherently than I suspect I will be able to do. Okay, so I want a continuous notion of a tree, and we don't really care about the vertices. What we're going to care about are things like shapes and distances, so geometric properties. So it's going to make sense to think of trees in terms of metric spaces. Okay, so the sort of notion that I want is the notion of what we call an R tree or a real tree. So a compact metric space TD is an R tree if for every pair of elements x and y of T, there's a unique shortest path, which I'm going to write with this funny square bracket notation, x, y, from x to y, which necessarily has length dxy, since it's a short path. And the only non-self-intersecting path from x to y is that short path. Okay? So in particular, I've got a unique path between 2 vertices that doesn't intersect. Okay, so I can write this down a little bit more formally in blue, but hopefully the description at the top was actually the thing that sort of made a little bit more sense kind of immediately. Okay, so a little bit of terminology. So an element V in T I'm going to call a vertex. A rooted R tree is simply one where I've distinguished a particular vertex to be the root, and I'll try to call that rho. The height of a vertex is simply its distance from the root. Okay? And a leaf is going to be a vertex which isn't on the path to anywhere. Okay? So it's going to be something that's at an extremity of my tree. Okay, so a very important way of getting an R tree is from a continuous excursion function. So this is my caricature of a continuous excursion. So this is a function which starts at 0 and ends at 0, is strictly positive in between, and is continuous. Okay, and what I'm going to do is imagine taking a glue stick and placing glue on the underside of the function. And then I'm going to think about squashing the two sides of the function together, and whenever two parts that have got glue on them meet, they stick together. That gives you a tree. Apologies to all of you who've seen this a million times before. I feel like I've been using this animation for a long time now. Okay, so let me just go backwards and point out a couple of things here. So these local minima of the function are going to translate into branch points in the tree. Okay. So formally, how do I do this? Okay, so I'm going to define a pseudodistance, so dh, which is obtained by, so the distance between the point x and the point y is obtained by summing up the value of the function h at x and y and subtracting off twice the infimum of the function between x and y. So what does that do? Well, I've shown you for various specific points in this, under this function, how this works. So let's think about points x and y corresponding to these local maxima here. Okay, so what do I do in order to get the distance between the point x and the point y? Well, what I do is I come down to the sort of local minimum between them, and then I go back up again. Okay, so that's giving me all of this distance plus all of this distance minus twice the distance up to the local minimum between them. Okay? And I can do that simultaneously for all of the points in my tree, and that gives me a pseudodistance. Okay, so let me show you 2 points which are at distance 0. So this point here and the point that's at the same height over here are at distance 0, right? Because they are achieving themselves the local minimum between them. Okay. So that's not very useful for something I want to be a metric, but I can just quotient out by it. Okay, so I'm just going to identify all points that this puts at distance 0, and that's going to give me a proper metric on the interval 0, 1. So let's take the quotient space 0, 1, quotiented out by this equivalence relation, which just puts y and y primed to be equivalent to one another if they're at distance. Okay, so then a theorem which I'm not going to prove is that if I take any such excursion function and I do this operation, what I get is an R tree. But I hope, at least from the pictures, it's reasonably clear why that ought to be the case. Okay, so there's a natural projection from 0, 1, from the interval onto the tree. Okay, and I'm just going to write pi h for that projection map. And I'm often going to root my tree at the image of 0, or equivalently 1. 0 and 1 are always necessarily going to get identified together because they're both, my value of the function is 0 at both. Okay, so I'm also going to want one more element of kind of structure here. I'm going to want to be able to sample points in my trees. So it's going to be useful to have a probability measure on my R trees. Again, there's a sort of natural way to do that, which is simply to take the uniform measure on 0, 1, so just the Lebesgue measure on 0, 1, and just see where that projects to on the tree under this projection pi h. Okay? So if I want to pick a point of th, my tree, according to this measure, all I need to do is sample a uniform random variable between 0 and 1, and then just see where the projection sends it. And that gives me a uniform point in the tree, or a uniform point in the tree. Okay, so I'm going to typically think of my continuous trees, my R trees, actually as triples of metric space, so space with its metric, and then with its measure, which is just this push forward of the Lebesgue measure onto the. So I realise that I've gone now quite far into stuff which I suspect feels quite technical if you're meeting it for the first time. So don't worry, there will be an opportunity to kind of absorb what's going on here, hopefully. Okay, so I want to be dealing with metric spaces which have this kind of tree-like property, which are endowed with a measure. And if I'm going to think about convergence to such an object, I'm going to need to have some sort of space and some sort of metric on that space. So here's the space. I'm going to think about compact metric spaces endowed with a Borel probability measure, so the sort of thing I've been talking about, considered up to measure-preserving isometry. right? So if two metric spaces are isometric, I don't want to think about them as being big, okay? Especially if the measure is behaving exactly the same on both of them. Okay, and I'm going to define a metric on that space, which is called the Gromov-Hausdorff-Prokhorov distance. Okay, and often we're going to be a little bit loose about this question precisely of isometry, because it's going to be useful to be working with a particular representative. Okay, but hopefully that won't cause any. Okay, so let me draw pictures, because I think that's the easiest way to understand this the first time. So here are two tree-like metric spaces. Okay, I hope you agree that they're sort of tree-like. Okay, and hopefully you agree that they look fairly similar to one another. Okay, so what I want to show you is the way in which these are similar in the Gromov-Hausdorff-Prokhorov. Okay, so if I've got two compact metric spaces, x and x primed, then I'm going to call a correspondence simply a subset of the product space such that for every x in x, there exists an x prime in x prime, which matches up with it, and vice versa. Okay, so I don't necessarily have a bijection between my two spaces, but everybody gets matched somewhere over here, or at least one place over here, and vice versa. Okay, so if I want to match these things up sort of similarly, I might do something like this. I might send the endpoint here to the endpoint there. I've got this little stubby branch here on the right that doesn't exist in the left. So maybe let's just send all of its points to something that looks like roughly where it's branched onto this larger stick, and so on and so forth. So hopefully the sort of matching up of points I've given you, obviously I haven't shown you every point in the space, but at least some of them. Hopefully that looks like a reasonable way to match these things up. Okay, and the distortion of a correspondence is simply how much does it change the metric part. Okay, so if I take the distance between x and y on the left, and I take the distance between a corresponding x primed and y primed on the right, and I compare the distances between them, then the distortion is the largest that that value can possibly be. Okay, so this is something that I want to make small in order to assert that my spaces are similar. Okay, and then I need to account for the measure. Okay, so suppose I've got a Borel probability measure on the left and a Borel probability measure on the right, so mu and mu primed. Okay, so by a coupling of those two measures, I mean a measure nu on the product space, which has as its marginals mu on the left and mu primed on the right. Okay, so this is just a way of making these two measures live together on this product space, x and x primed. And in principle, I can do that any way I like. I could take the marginals to be independent of one another, for example. Now, that's not what I'm going to want to do. What I'm going to want to do is match up the measures so that they behave as similarly to one another as I can make them do. So the idea here is going to be to find a correspondence and a coupling such that the correspondence has got small distortion, so distances are looking similar in the left picture and the right picture, and the coupling lines up well with that correspondence in the sense that if I pick according to the measure nu, then that's most of the time hitting the correspondence. Okay, so the probability that I'm sampling from within the correspondence is close to 1. And if I can do those two things, then we'll say that my two spaces are close to 1. Mm-hmm. Oh, good Lord. Can I think about that one afterwards? The average is simpler, but it's not going to... Then we're potentially going to have points which do weird things. Okay, that's an extra condition. Maybe let's think about that one afterwards. Okay, so let me define the Gromov-Hausdorff-Prokhorov distance between two spaces x d mu and x prime d prime mu prime then. So this distance is going to be half for reasons of an equivalent definition that has a factor of 2. The infimum over possible correspondences and possible couplings, so correspondences R and couplings nu, of the maximum of the distortion and the measure of the complement of the correspondence. Okay, so I want us to be not putting much probability mass outside the correspondence, and we want to have small distortion. And if we can achieve both of those things simultaneously, then we're saying that our spaces are closed. So, theorem, which again I'm not going to prove, but I've given you some references here. This is a complete separable metric space, so it's something that we can do probability on. Okay, if that weren't the case, we'd be in trouble at this point. Okay, so we've got a way of comparing metric spaces which are endowed with a measure, and I now want to apply this to the sort of setting that we were thinking about. So I want to apply this to show, or at least talk about, the sense of the convergence of these binary trees. So before I do that, let me finally give you a definition. Okay, so the Brownian continuum random tree is the R tree that we get by doing this whole construction with a continuous excursion function, which is simply the standard Brownian excursion. Okay, so for those of you who've met a Brownian motion but not a Brownian excursion, so let me draw a Brownian motion badly because all pictures of the Brownian motion are bad. Okay, so let me pick, say, time 1. Okay, with probability 1, time 1 is going to fall inside, in the interior of an excursion away from 0. Okay, and I happen to have picked a negative excursion just to make my life more complicated. Okay, so this excursion here, in which time 1 sits, has a random length, but I can do the Brownian scaling to it. So I want to scale space with the square root of the scaling that I applied to time. Okay, and that gives me an excursion function, which I'm going to flip up the other way just to make things complicated. Okay, so which spans the interval 0, 1. And that's one way of constructing a standard Brownian excursion. So just extract any one of these excursions that you like, but let's take the one that straddles time 1. Okay, scale it so that it has the correct length and flip it up the right way if it was the wrong way up to start. Okay, so if you do that, you take the continuous excursion function that gives you, and then you do this gluing operation to the standard Brownian excursion, what you get is the Brownian continuum random tree. Okay, so I haven't at all told you why that's the same thing that we got out of the line-breaking construction, but in a sense that's going to be a consequence of what I now say. I want to first observe that this excursion comes with more information than the tree in principle. I'm thinking about the tree now just as a sort of metric space. It doesn't have a notion of left and right, but the excursion does. Right? So if I've got a time s, which is here, and a time t, which is there, and I suppose those both happen to give me leaves in the tree, then I kind of feel like the one to the left is to the left of the one to the right. Okay, so in fact the excursion is giving me a little bit more structure. It's giving me a sort of planar ordering on the leaf. Okay? That's also something that we had in Rényi's algorithm, right? We had a planar ordering on our leaf. Okay, so I want to think of my binary trees as metric spaces now. And there's sort of a natural way to do that. Okay, so firstly I've got 2 or indeed 3 sorts of vertices here. I've got the root, okay, which was playing a kind of special role. I've got internal vertices, and I've got leaves. Okay, but let's just think of them all interchangeably as vertices, okay, and just use the graph distance to tell me how far apart they are. Okay, so what do I mean by the graph distance? I simply mean how many edges do I need to traverse to go from one to the other. So the distance between 4 and 7 here is simply 3, because I need to traverse 3 edges in a shortest path between 4 and 7. Okay, so there's a natural distance on any graph, the graph distance. Okay, I'm sometimes going to write a times tn as a sort of abusive notation for the metric space, where I take the same space, but I scale all the distances by a factor of a. Okay, so that's just going to be sort of convenient notation. Okay, and here I'm thinking about the points of my space as simply being the vertices of my tree. Okay, so I'm thinking of this as a metric space which simply has 2 endpoints, okay, consisting of the vertices, and I'm using the graph distance to tell me how far apart. So I hope that's clear. Okay, So I'm going to endow this tree with μn, the sort of obvious uniform measure, which just puts mass 1 on 2n on each of the vertices. Okay, so there's an obvious measure, uniform measure on such an object. Okay, so then my claim is that as n goes to infinity, if I take this binary tree and I take the graph distance and divide it by the square root of 2n, so the scaling that we saw earlier for distances between points in the object, and endow it with this uniform measure, then I'm getting convergence to the Brownian continuum random tree almost surely with respect to this Gromov-Hausdorff-Prokhorov. So how does this go? How do we go about proving this? So we need to somehow show that the Gromov-Hausdorff-Prokhorov distance between these two things is getting smaller and smaller. Between left and right is getting smaller and smaller as n goes to infinity. Okay. So let me start by reminding you or showing you a bijection between planted plain binary trees with n leaves and lattice excursion. So those of you who are familiar with this sort of Catalan world will know this well. So these are both things enumerated by the Catalan numbers. Okay, so on the left, I've got a lattice excursion, and on the right, I've got one of the sort of trees that I'm interested in. Okay, so what I'm going to do is, starting from the tree, I'm going to start every excursion with a +1 step, and then simply I'm going to do a depth-first exploration of this tree, and whenever I encounter a non-leaf, I'm going to go up by 1, and whenever I encounter a leaf, I'm going to go down by 1. Okay, so the steps of my walk are all simply going to be up and down. Okay, so let's do that. So we make a +1 step to start. Okay, I'm at a non-leaf, so I need to make a +1 step. Non-leaf +1, non-leaf +1, leaf, down 1. Leaf, non-leaf, so up 1, and then so on and so forth. So you can see that every time I'm at a leaf, I'm making it down. Okay, and I'm just doing the usual depth-first exploration of the tree. Is there anybody for whom that's not a familiar concept? I'm happy to talk through what it is. Speak now. What do you mean? I mean, that's a binary tree, isn't it? With plain trees, I see. Okay, well, I want to do it like that. Okay. So I want to show you that I can go back. So I just showed you how to go from tree to excursion. Okay, so to go back the other way, okay, I've put the labels back on, but they're not really important here. Okay, so there's how you go back the other way. Okay. So I hope it's clear that there's only one tree that I'm going to get back to this thing. Okay. I think this is quite nice because I think it shows you a couple of things. So firstly, I mean, it's clear that you've got a correspondence here. And since the trees are uniform, so must the lattice excursions be. Right? I've got two sets which are enumerated by the same, they have the same size. I'm picking uniformly from one, that must correspond to uniform from the other. So this must be just an excursion of a simple random walk away from 0. Okay? So at least in distribution, that's precisely the sort of thing that ought to be converging to a standard Brownian excursion if I rescale it correctly. Then goes to infinity. Now, I claimed an almost sure convergence, so there's something a little bit more delicate going on here. But at least distributionally, it's obvious that hopefully sort of clear that that should be the right limit. So Rényi's algorithm is really then, and this is very much due to Philippe, Rényi's algorithm is then corresponding to a kind of sequence of simple operations on these lattice excursions, which just makes them grow. Okay, and let me just show you it. I'm not going to describe it in detail, but this is what it's doing. So this is Rényi's algorithm on the tree on the right, corresponding to a sequence of kind of operations on these lattice excursions. Okay, and Philippe's theorem is that if you do this sequence of operations on these lattice excursions, then in fact you're getting almost sure convergence to a Brownian excursion, rather than just the distributional convergence, which is hopefully kind of clear from the fact that we've just got simple random walk excursion. Okay, so this is not quite enough to conclude that the trees are converging in the Gromov-Hausdorff-Prokhorov sense. So this is certainly a suggestion. Right? We've got some sort of coding excursion, which is in correspondence with our trees, okay, and that excursion is converging. That's not quite enough to tell me that I've got convergence of the trees. And one reason for that is that the way that I've embedded this tree in the excursion is distorting the distances. And you can actually see that very clearly in this picture. Right, so here on the right, you can see the graph distances very clearly. And this distance between 0 and 5 has somehow got very stretched by comparison with what's going on the right-hand side here. And it turns out that the stretch factor is sort of approximately 2 in the limit. Okay, so if I write hn of k for the distance from the root to the vertex that I visit at time k when I do a depth-first exploration of my tree, so that distance is looking approximately like twice this excursion at the same time. Okay, so then I'm going to get convergence of this so-called height process. So I'm just asking, as I explore my tree, how far away from the root is the point that I'm currently exploring? Remember, I'm doing my exploration in a sort of depth-first manner. Okay? Then I'm getting convergence on rescaling in the correct way to twice a Brownian excursion. And again, almost surely, rather than just distributionally as you might think. Okay, so I've got about not very much time. I want to get through to the end of this chunk, and then maybe we started a little bit late, so maybe I'll take some questions at the end. Okay, so I should mention Jean-François Marca and Abdelkader Mokadem in this context. This is the fact that you can get convergence to the same quantity here, this excursion on the right-hand side, being the same excursion as the one which the lattice excursions converge to is due to them. So I want to talk about the trees converging. So I've talked about these coding functions converging, okay, and I've said that's not quite enough to get the tree. So let's see how this translates into a convergence for this Gromov-Hausdorff-Prokhorov distance. So we've got 2n vertices, and we've been thinking about exploring the tree in a sort of depth-first order. Okay, so let's call these vertices v0, v1 up to v2n minus 1 in depth-first order, okay, where v0 is just going to be starting from the root. Okay, so this hn, so this height process, is simply telling me how far am I in the graph distance away from the root at vertex vk. Okay, now more generally, if I take two indices I and j between 0 and 2n minus 1, let me write vi min vj for the most recent common ancestor of vi and vj in the tree. Okay, so it's just a fact about trees that this is the case. Okay, so the distance between vi and vj I can obtain by take the distance back to the root for each of them and subtract off twice the distance from the root to the most recent common ancestor. So let me just draw a quick sketch. Okay, so here's vi, here's vj, here's vi min vj. And to go this distance, I can equivalently go down to the root, back up again, and subtract off twice this. Okay. Now, this distance from v0, from the root, to vi min vj, well, it turns out you can express that in terms of this height function. Okay, so let me start with the easy case. If vi is an ancestor of vj, then it's simply the minimum that the height function attains between I and j, because it's just whichever of them I've visited first. Okay, and I don't go lower than that before visiting the other. And if, on the other hand, vi is not an ancestor of vj, it turns out we're one off that minimum between I and j. Now remember, I'm going to rescale everything, so making an error of -1 is really not serious here. Okay, so why is that? Well, if you think about doing this depth-first exploration, I'm going to get to vi first, okay? And I'm going to visit some stuff potentially on the right here, and then I'm going to visit this vertex on my way up to vj. Okay, now I've already visited the most recent common ancestor of them on my way up to vi the first time. So I'm sort of off by 1. I get quite close to revisiting it, but I've already done it once, so I'm not going to do it again. Okay, so that's where this -1 comes from. Okay, so let's actually build ourselves a correspondence and a coupling. Okay, and if we can do that sufficiently cleverly, we'll get a small distance between our two spaces. Okay, so we've got these vertices v0 up to v2n minus 1. Okay. On the other hand, I would like to take 0, 1. Now, eventually I'm going to quotient out, but let's for the moment deal with 0, 1 because that's easier. Okay, so I'm firstly going to say that vi and s correspond to one another simply if I is the floor of 2n. Okay, so I'm just going to split the unit interval up into chunks. Okay, equal size chunks. Those are going to represent my vertices, or at least those are going to correspond to my vertices. Okay, 0, 1's got this natural pseudo-distance d2e, okay, which is just given to me by the standard Brownian excursion, or in fact twice the standard Brownian excursion because of the convention that I took. Now let's bound this distortion. Okay, so let's suppose that we've got two pairs in my correspondence, vi, vj, and they correspond to s and t respectively. Okay, where s is less than or equal to t, or equivalently I is less than or equal to j. Okay, so what's the difference between the graph distance between vi and vj on the left and the d2e distance on the right? Well, one of these things, I've taken the rescaling already, is simply given by this quantity up to potentially my error of -1 caused by being off from the most recent common ancestor. But I've rescaled everything, so I've multiplied everything by 2 and I've rescaled by a factor of square root of 2n. That's going to give me some negligible factor at the end there. And then, of course, this is the pseudo-distance that was given to me by twice the Brownian excursion. Okay. So this right-hand side is just converging to 0 uniformly in S and T in 0, 1. And so the distortion is going to 0 almost surely. Okay, because we had almost sure convergence of this height process to twice the standard Brownian excursion. Okay, so that deals with the distortion. How about the coupling? I don't really mind though. Okay, so suppose we've got our uniform measure on the vertices, so mass 1 on 2n on each of the vertices. So then I can couple these things simply by taking a uniform random variable on 0, 1, and then taking v, the floor of 2nu, okay, on the left-hand side, and on the right-hand side, just the projection on the tree of that uniform point. Okay, so what I did was took precisely the coupling that was given to me by the correspondence. Okay, so this thing never puts any mass outside the correspondence because by construction it's all within the correspondence. Okay, so nu n of the complement is just 0. Okay, so all I actually need is that the distortion goes to 0, and that gives me that the Gromov-Hausdorff proper distance goes to 0. Okay, so then we get almost sure convergence of our trees with their measures to the Brownian continuum random tree with it. Okay, so I've told you for a story for a specific family of random trees. And what I'd like to talk about now is how this really isn't as specific as all that. It works for a much more general family of random trees. So I want to talk about universality, to borrow a word from physics. Okay, again, Jean-François. Let me remind you what I mean by a branching process. So a Bienaymé-Galton-Watson branching process, let's call it Zn. This is describing the evolution of the size of a population that evolves as follows. I'm going to start with a single individual. Okay, that individual's got a random number of children distributed according to something I'm going to call the offspring distribution. So this is something with a probability mass function p. Okay. Each of those children is then going to independently reproduce with the same distribution as its parent did. Okay, so I've got the same offspring distribution at each stage. So Zn is going to give me the number of individuals in generation. So I'm always going to start my branching processes from a single individual, although obviously you can do more general things. Okay, so I'm going to call a BGW tree the family tree that arises from such a branching process. So let me just draw a picture. So I'm going to start from my single individual, and maybe I'll use the Ulam-Harris notation here for the names of the vertices. So we start with the empty set, labeling the root. Okay, so this is going to have a random number of children, let's say 3, and I'm going to label them 1, 2, 3. Okay, and then let's look at the children of number 1. Okay, so suppose it has 2 children. I'm going to label them 1, 1 and 1, 2. Okay. 2 has a single child, say 2, 1. So I just want to sort of make it clear what my notation is. Okay, and suppose nobody has any more children. This thing dies out at this stage. Okay, so I want to think about this as a plane tree so that I can distinguish, so first child, second child, and third child, and I draw them across the page in that order. Okay, so I hope it's clear the sort of trees I'm going to be thinking about here. Okay, so I'm thinking of these as rooted ordered trees. Okay, so I'm going to specifically look at the case where the offspring distribution is critical, so it has mean 1. So those of you who've seen branching processes before will know that if the mean is at most 1, then the tree is finite with probability 1, and if the mean is bigger than 1, at least in non-degenerate cases, then we've got probability positive of having the tree just keep growing forever. Okay, now I'm interested in finite trees, so let's take, in fact, the critical case where we've got precisely mean 1 for the. Okay, so this captures, in disguise, quite a lot of combinatorial trees. So the case that we've been thinking about up until now, at least if I remove the plant edge, is simply what you get if you take the offspring distribution to put mass 1/2 on 0 and mass 1/2 on 2, and then you condition the tree to have total size 2n minus 1. So 2n minus 1 vertices. So then that tree is uniform on the set of rooted but unplanted plain binary trees. Okay? And it's obvious how to get back and forth between those two models. I just stick an edge on the bottom. Okay. If I take a geometric 1/2 offspring distribution, then it turns out that what you get is uniform on the set of plane trees with n vertices. Okay. And again, checking these things is going to be on the example sheet this evening. Okay. And then something that's going to be important for my second lecture is what happens if you take a Poisson 1 offspring distribution. Okay, so here this is a slightly more complicated thing. So I'm going to take a Poisson 1 BGW tree, conditioned to have total size n, and then I want to do something extra to it. I want to assign its vertices, which in principle have these Ulam-Harris labels, a second label, which is just an integer chosen from 1 up to n. So what I want to do is assign the vertices of this tree a second labeling, which is just chosen uniformly at random from the possible labelings by 1 up to n. Okay, and then I want to forget the original labeling and the fact that I was looking at plane. Okay, so that then turns out to give you a uniform random labeled tree, so a Cayley tree. Okay, so the set of things that are enumerated by n to the n minus 2. So that's going to be important in tomorrow's lecture. So if I now... Sorry? Yikes, I don't know. What sort of trees do you want labelled only on the leaves? So I just gave this extra labelling, and I'm sort of not very interested in that because it doesn't really change the law of the tree, right? Because I can just sort of ignore it again later. It was a sort of second uniform element. It didn't really interact with the first. Yeah. Okay. So if I take Tn now to be the family tree of a BGW process with critical offspring distribution, which has finite variance, and this is important, and it needs to have a finite variance. So let's condition such a tree to have total progeny n, so n vertices in total. Okay. Let's take dn again to be the graph distance, as we did before, and let mu(n) again be the uniform measure on the vertices. Then the theorem, which in various versions is due to sort of Aldous and Legal, is that if I take Tn, I rescale the graph distance by sigma on square root of n, and I just take the usual uniform measure, then I get convergence in distribution again to the Brownian continuum random tree, again in this Gromov-Hausdorff graph. This is much more general than what we just saw in the first section. Okay, it certainly includes the result that I've just proved to you. Let me observe that this is a convergence in distribution now. So in the first section, we had an almost sure convergence, and that's not the case in general. So the binary case is special in that you can construct everything nicely on the same space in such a way that you're getting convergence almost surely. Okay? Here in general, we've just got convergence in distribution. Okay. So we've seen that it's convenient to encode our trees in terms of discrete functions because they're kind of easier to manipulate than the trees themselves. And we saw how to use kind of correspondences and couplings in order to get from those sort of functional encodings into a convergence statement for the trees. And I'm going to think about doing this encoding in two different ways for the purposes of sort of discussing how one goes about proving this theorem. And I'm in danger of, might have to stop in the middle of this, but we'll see. Okay, so I want to do this encoding in two different ways. So I want to talk again about the height function, which we've just saw in the previous section. And I want to talk about a depth-first walk, which I think is a Łukasiewicz path, but I'm so bad at pronouncing it that I'm going to call it the depth-first walk. Okay, so again, suppose we've got a tree with n vertices. We're going to label the vertices again in depth-first order as v0 up to vn minus 1. Okay, and again, the height function is just how far are we away from the root when we visit vertex vk. Okay, so let me just sketch this out for a little tree. So here's a tree that I've labeled in a similar way to there. Okay, so I'm just doing the depth-first exploration of this tree, and I'm just recording how far away am I from the root. Okay, so it's clear that I can get back from that height function to a tree. Okay, so this is something that I think you can probably do in your head. Okay. For the depth-first walk, I just need one more bit of notation. Thank you. So let's see if v be the number of children of v, okay, for a vertex v. And again, we've got our vertices listed in the same order. So let's define a process by x of 0 starts at 0, and at every step, what am I going to add on? The number of children that I'm currently visiting, or sorry, the number of children of the vertex that I'm currently visiting, minus 1. Okay, so this is actually doing exactly what we were doing in the binary case, because whenever we saw a leaf, we were subtracting 1, and whenever we saw a branch point, well, it necessarily had 2 children, and so we were just adding on plus 1. Okay, so this is the generalization of that. Okay, so let's sketch it out for this. So the root has a single child, so add on number of children minus 1, we get 0. Okay, 2 children, go plus 1. 2 children again go plus 1, minus 1, and so on and so forth. Okay, so we've got the depth-first walk of this tree. And notice that we're always going to end up at minus 1 at the end of this, because what did we do? We summed up the number of children, minus 1 each time. The number of children in the whole tree is necessarily going to be n minus 1, and the number of vertices was. Okay, so the proposition, which is again going to be on the example sheet this evening, is that the height process can be obtained from this depth-first walk. And so in particular, you can get back the tree, even though you can't really see it very easily, from this depth-first walk. So if I can get back to the height process, I can get from the height process to the tree. Okay, so remember that we had our offspring distribution with probability mass function p, which was critical. Okay, so suppose I take a random walk, which starts from 0 and has as its step distribution just the offspring distribution shifted by 1. Okay, so the probability that I make a step of size k is the probability the offspring gives me k 1. Okay, so I'm just shifted by minus 1. And let's think about m being the first time this random walk hits minus 1. And now let's take, on the other hand, my Galton-Watson, I was trying to call it BGW tree, with offspring distribution p and total progeny n. So then my claim is that its depth-first walk has the same distribution just as this stopped random walk. Okay, so in particular, the depth-first walk is a distributionally nice object. It's just a random walk that I've stopped at the first time it hit minus 1. And I think that's probably a good place to stop. So if you want to see a careful proof of this, see the paper of Legal. Okay, thank you.
Est-ce qu'il y a des questions pour Christina?
In either language. I still don't know the answer to his earlier questions.
Well, that's
That's not an innocent question. It's a question oriented towards things that I need in the future. How bad is, suppose that we have this theorem already in our set of tools, and works are in 1+1 dimension. Say that you have extra dimensions in which the work is also moving. There are extra parameters that evolve. Is it for free that I can do this convergence also for the extra variables which are there, supposing that they are evolving in a smooth way with a martingale or whatever, or do I have to start from scratch?
I'm not quite sure I understand your construction.
Say that on
so you want to have a tree converging with extra structure on top of it somehow?
Extra structure on the vertices of the tree.
Okay.
And extra structure on the nodes of the work that you are transporting in a bijective way somehow. And then I want to say that the continuum object exists also with the extra structure. Doable to be seen.
I mean, it sounds plausible at that level. I mean, obviously not without conditions. I mean, something will be true there, but I mean, without knowing sort of more precisely what sort of thing you want. I mean, subject to being able to come up with a suitable topology, then in principle, yes, right? I mean, but I mean, arbitrary things aren't going to converge. So
you don't have ideas of application in which this was already happening all the time? No.
I mean, yes, I mean planar maps, but maybe you can tell me more detail afterwards what you mean.
Est-ce qu'il y a d'autres questions?
Just quickly, so the reason you ask the expectation of the degree be equal to 1 is because you want to be in the middle of some, I don't know. Why do you ask for average degree to be equal to 1?
Okay, because that gives me a particularly nice realization of some of these combinatorial trees. And so, I mean, the motivation is really, let me go back to the relevant slide because it went by quite quickly.
Is it because you want to link it later to some critical phase of transitions in graphs, or that's not the reason?
Well, I mean, that is also another reason. So that turns out also to be the right class of things to look at in that context also. But suppose I want to construct these. So some of these things I can construct by taking subcritical offspring distributions, some of them I can't. But which setting gives me the largest chance of getting a tree of size precisely n? So if I have a subcritical setting, the probability of getting a tree of size n is generally going to be exponentially small. And here it's only polynomially small. So in some sense it makes sense if you want to condition a tree to have size n to be sitting in the case where that probability is already large.
Okay, thank you.
Sinon, je propose de remercier Christina pour cette première partie de cours.
Merci.